Hello everybody. In this session, we are going to think about transistor biasing circuits. At the end of this session, students will be able to analyze fixed biasing circuit and collector to base biasing circuit for a transistor operating in common emitter amplifier. These are the contents of this presentation. So, let us go for the first type of transistor biasing circuit. Now, this figure shows the circuit diagram for common emitter transistor amplifier in which fixed biasing circuit is used for biasing the transistor. In fixed biasing circuit, as shown in this circuit diagram, the base biasing voltage is obtained from a VCC and using fixed resistor RB, base resistor RB. So, circuit is designed around base and collector circuit. So, that is usually a transistor like a N-PN transistor that is shown in this circuit diagram. Amplifier is operated on a single DC power supply. So, both the junctions of transistors are biased using a single positive DC voltage power supply VCC as far as N-PN transistor is concerned. So, the minimum voltage required to forward bias a base emitter junction, that is the cut-in voltage, and to set a desired value of base current IB and corresponding to that a collector current IC, the base biasing voltage is obtained using a same DC power supply plus VCC. So, using plus VCC and base resistor RB, the required positive voltage is applied at the base of transistor with respect to ground. So, depending upon value of VCC and value of RB, desired value of base current IB is set, and corresponding to that collector current IC is set under DC working condition, and corresponding to that collector to emitter voltage will set. So, here the input AC signal that is to be amplified at the input of base terminal of transistor through coupling capacitor, and output is taken from collector. So, in fixed base biasing circuit, as plus VCC is constant DC voltage and RB is a constant resistor, fixed resistor. So, value of IB flowing through the base terminal of transistor is also fixed. So, that is why such a biasing circuit is called as a fixed biasing circuit. It is the simplest biasing circuit for a transistor using a minimum number of components. So, using single resistor between VCC and base terminal of transistor, this biasing circuit is constructed. So, VCC, RB are fixed, hence the base current IB is also fixed. That is why this biasing circuit is called as a fixed biasing circuit. So, this fixed biasing circuit cannot automatically keep the IC constant to stabilize the quick Q point against a temperature change. So, whenever any change in the collector current, that is due to change in reverse saturation current, so that depends upon temperature, there is no any change in base current IB, IB remains fixed. So, IB cannot automatically control the value of collector current IC. So, it cannot this biasing circuit cannot automatically keep IC constant to stabilize the Q point against temperature change. So, fixed biasing circuit does not provide any stability to the DC operating point or quiescent point of the transistor common emitter amplifier using fixed biasing circuit. Now, let us go for the DC analysis of this common emitter transistor amplifier using fixed biasing circuit. Using DC analysis, let us obtain the values for a quiescent point or Q point like VCQ and ICQ, collector to emitter voltage at Q point and collector current at Q point under DC working condition. So, let us first go for the collector current ICQ at a Q point. Consider the figure number 1, circuit diagram in the figure number 1. Apply KVL to the base emitter circuit, input circuit of this amplifier. Starting from VCC, let us go in a anti-clockwise direction starting from VCC. So, whenever we go from lower potential to higher potential, take a positive sign, and whenever we go from higher potential to lower potential, take a negative sign. So, let us write a voltage equation around a base emitter circuit of a transistor starting from VCC. So, VCC minus voltage drop across base resistor RB, that is IBRB minus IBRB, minus voltage between base and emitter, that is a cut-in voltage of a transistor. So, that is minus VB equal to 0. So, from this we can write the equation for a base current IB, DC base current IB under DC working condition, IB equal to VCC minus VB upon RB. Since the value of VB that is about 0.6 to 0.7 volt for silicon transistor and 0.2 to 0.3 volt for germanium transistor cut-in voltage, once transistor is turned on, the voltage between base and emitter VB remains approximately constant, and that value is very small as compared to the value of VCC. So, the value of base current IB can be approximated to VCC upon RB, neglecting the value of VB. So, IB will decide the output collector current IC. We know that IC is equal to a beta times IB, where beta is the current gain of transistor in common emitter circuit configuration. So, output DC collector current IC equal to beta times beta into input base current IB. So, using these two equations, we can calculate the value of DC collector current at Q point ICQ. So, that is equal to beta times IB. Now, let us go for the another coordinate of DC operating point Q point, that is VCQ, collector to emitter voltage at a Q point. Consider figure number 1, again same circuit diagram in the figure number 1. Use KVL to collector emitter output circuit. Starting from VCC, let us go in a anti-clockwise direction. VCC minus voltage drop across collector resistor RC minus ICRC minus collector to emitter voltage, voltage between collector and emitter across the transistor minus VC equal to 0. So, this can be written as VCC equal to total voltage given to collector emitter circuit of a transistor, VCC equal to the some part of this voltage will appear across RC. So, that is ICRC plus the voltage remaining part of that VCC will appear between collector and emitter of a transistor, that is VC. So, just we have rewritten the previous equation. Then collector to emitter voltage, we can write this equation for collector to emitter voltage VC equal to VCC minus ICRC. So, using this equation, we can determine the value of DC voltage at a collector with respect to emitter, that is the ground, under DC working condition VCQ equal to VCC minus ICRC. So, from this we can obtain the values for Q point, that is VCQ and ICQ. Now, let us consider stability factor for this fixed biasing circuit. In general, stability factor for a Q point of a transistor in common emitter circuit configuration is given by S equal to 1 plus beta upon 1 minus beta into derivative of base current IB with respect to derivative of collector current. So, in fixed biasing circuit, if there is any change in collector current that does not cause any change in base current, so base current is fixed for a fixed biasing circuit. So, base current will not change to control the value of collector current. So, change in base current due to change in collector current for a fixed biasing circuit is equal to 0. So, stability factor S, designated as S for fixed biasing circuit, is given by S equal to 1 plus beta. Since change in IB due to change in IC, due to that is due to change in temperature is 0. So, S is equal to 1 plus beta. The value of S is very large because value of beta is generally very large value, that is the current gain of transistor in common emitter circuit configuration. So, fixed biasing circuit provides a very poor stability to the Q point since value of S is very large. So, any change in collector current, any change in temperature, that is reverse saturation current, corresponding change in collector current, so that is indicated by stability factor. Stability factor S indicates the change in collector current due to change in reverse saturation current, that is due to change in temperature. Now, let us go for the second type of transistor biasing circuit. whenever transistor is connected in common emitter amplifier. So that is the collector to base bias circuit. So in collector to base bias circuit, the base biasing voltage is obtained from collector of transistor using a single resistor RB. RB is connected between collector and base of a transistor. Base biasing voltage is obtained from collector using base resistor RB. So this collector to base bias circuit can automatically keep IC constant to stabilize the Q point against temperature change. So in this collector to base biasing circuit, voltage shunt negative feedback is used. So using a proper value of RB and RC, you can set a desired value of base current IB. Corresponding to that, collector current IC is set under DC working condition. So let us think about the stabilization of Q point. As temperature increases, reverse saturation current increases, and due to that, collector current increases. So voltage drop across collector resistor RC increases, that is IC into RC increases. So collector to emitter voltage VC decreases since VCC is constant. So as collector to emitter voltage decreases, the base current IB decreases since IB is given by VC minus VB upon RB. So this reduces the IC, collector current IC, because IC is given by beta times IB. Thus, the initial increase in collector current is compensated, and the initial value of collector current is restored, comes to initial value, and Q point is stabilized. So let us obtain Q point values for collector to base bias circuit. First, let us go for ICQ. Apply KVL to base emitter input circuit. So VCC equal to IB plus IC into RC plus IB into RB plus VB. Current flowing through collector resistor is the sum of base current and collector current. So IB equal to IC upon beta, that is equal to VCC minus VB minus IC RC upon RB plus RC. So IC equal to beta times IB. So IC alternate equation for IB, VC equal to IB into RB plus VB. So IB equal to VC minus VB upon RB. Now let us obtain equation for VCQ. Apply KVL to collector emitter output circuit. VCC minus into bracket IB plus IC into RC minus VC equal to 0, or VCC equal to IB plus IC into RC plus VC equal to 0. Therefore, VCQ equal to VC equal to, that is collector to emitter voltage, VCC minus IB plus IC into RC, and we get the coordinates for a quiescent point VCQ and ICQ. Stability factor for a collector to base bias circuit. So in general, stability factor is given by 1 plus beta upon 1 minus beta into a derivative of base current with respect to collector current. So differentiating this equation with respect to collector current, so derivative of base current, change in base current due to change in collector current is equal to minus RC upon RB plus RC. So stability factor, substitute the value of this in the previous equation. Stability factor for collector to base bias circuit is given by S equal to 1 plus divided by 1 plus beta into RC upon RB plus RC. Since value of S is much smaller than a fixed bias circuit, stability of Q point is better for collector to base bias circuit. Student can pause video here and think over this question and try to answer this question. So what will be the value of S if beta equal to 49 for fixed bias circuit, and what is this value indicates? If beta equal to 49, then S equal to 50 for fixed bias circuit. It indicates IC changes 50 times as large as change in reverse saturation current, that is due to change in temperature. So this is the reference. Thank you.